we're indeed changing pace a little. I'm going to talk about numerical algorithms. And I'm going to sort of talk about two topics, which are related. One is kind of generally compact representations, in particular sum-of-exponentials representations of imaginary time functions. And then I'll talk about an application of that technology to evaluating Feynman diagrams. So this was joint work with a few different people. Sort of the first part on compact representations of imaginary time functions was with Kun Chen and Olivier Parcolet. And then the second part on diagrammatics was with Zhen Huang, who's a PhD student at UC Berkeley, graduating soon, as well as Hugo Strand and Dennis Golesh. Okay, so what's the overview? Just move this. So I think over the past few years, there have been more and more algorithms kind of using this technology of compact sum of exponentials expansions of imaginary time objects, the Green's function, self-energy, hybridization, not only sort of to make faster algorithms, but also to make algorithms that have controllable accuracy and are kind of robust and automated. And I want to identify two categories of these algorithms, which I think is useful. One is what I'll call kind of universal discretizations. The discrete Lehmann representation will be my example of this. So there, you want sort of a single representation that works for all basically imaginary time functions at the same time, and it will become clear what I'm talking about. And then there's another category of algorithms where your goal is for a given function to come up with the most compact possible sum of exponentials expansion. And there have been some algorithms sort of from the applied math community which have made their way over here. AAA, Prony's method, ESPRIT, which can do that for you. And I'll talk a little bit about AAA. So then I'll talk about this application, which is a fast deterministic method for evaluating diagrams for, in our case, a bold hybridization expansion of an impurity model. We're going to try to get, in the end, sort of an impurity solver, which can deal with very general hybridization functions, scale mildly with temperature as you lower the temperature, and sort of deliver high-order user-controllable accuracy at a fixed diagram expansion order, so there's no Monte Carlo here. We're not going to try to completely eliminate the kind of combinatorial and exponential scalings that appear in evaluating diagrams up to a given order, or try to sample all diagram orders, but we are going to sort of lower the rate of exponential scaling up to a point where we can go beyond the kind of very low diagram orders which have sometimes been used, and time will tell for how many problems this is enough. So, okay. Let me get into the first part on compact representations of imaginary time functions, and I'm going to tell you about this method we developed called the discrete Lehmann representation. So here I'm writing G for Green's function. The same thing sort of works for hybridizations, which I'll use them on later, and self-energies and other imaginary time functions. So we know that the Green's function satisfies this integral representation called the Lehmann representation or spectral representation, where rho is a spectral function, which we take as compactly supported with some bandwidth. And this integral representation involves this nice exponential kernel, okay? So every G has a rho, such that this is true. And basically what we can do is, let's say, take this kernel, densely discretize tau and omega. So you can think of this as a matrix with rows tau, columns omega. And then you look at the singular values of this matrix, and you see that they sort of decay actually super exponentially, so that in some sense this kernel is very numerically low rank, okay? And what that means is, using an algorithm, which I'm not going to go into detail, we can choose sort of the most linearly independent columns Okay, so we choose a subset of the columns which form a basis of the column space. Okay, what's the column space of this? Well, it's the space of sort of all possible G's, okay, for different rows. And what does it mean to subselect columns? Well, it means to select special frequencies omega L. So in the end, what this gives us is sort of a discrete version of this Lehmann representation, which we call the discrete Lehmann representation, or DLR. Namely, we see that there's some omega L's we can choose, which very importantly only depend on the kernel here. Okay, I only sort of needed to subselect columns of the kernels to represent the column space of the kernel. They don't depend on rho, but there are some frequencies omega L such that for any G, you have a representation of this form for some coefficients which depend on G. Okay, so I'll kind of repeat that again in a second, but we get this sum instead of integral representation here. K tau omega L is this exponential kernel. Okay, so again, more specifically, given an inverse temperature and a frequency cutoff on our spectral function, there's a basis of the space of all G's, which satisfy this cutoff, okay, which we can make accurate to some user-specified epsilon, okay, such that we have an expansion of this form for some coefficients GL. Since the kernel is numerically low rank, it turns out that the number of basis functions we need only scales logarithmically in this basically dimensionless product. So basically logarithmically with the inverse temperature at fixed bandwidth. And this is very nice. You can compare it with what we would need for an equispace grid representation, which from staring at this the Lehmann representation, you can figure out would be linear in the inverse temperature. Okay, so that's a big improvement. Very good. So just to give a visual example, this is sort of what a typical imaginary time Green's function would look like. At beta equals 100 with omega max bandwidth 1, we need 26 basis functions to capture this entire space at 8-digit accuracy. At beta equals 10,000, it's 59, and beta equals 1,000,000, we get these very sharp functions, but we only need 92 degrees of freedom to capture this whole space. Okay, so this was sort of based on or kind of an extension in some way of earlier technology introduced by Hiroshi Shineoka and his co-authors called the intermediate representation, or IR. So if you've heard of that, basically they compress this kernel using the SVD, and that means that they take as their basis of Green's functions the left singular vectors of this kernel, whereas we take as our basis selected columns of the kernel. And what that means is in the end, the IR is an orthogonal basis, but the basis functions are not explicit. They're not exponentials like this, whereas our basis is non-orthogonal, but we get an exponential basis, which we like for reasons which you'll see. So, okay, there's also an interpolation grid, which allows us to recover these coefficients GL from samples of G at the interpolation nodes, which are here. If we want to compute, for example, products of imaginary time functions, we can do that by just multiplying their values on this grid and then forming the expansion by interpolation. And if we want to do operations, for example, later in the talk, we're going to need convolution, this kind of like convolution up to time tau. We can just plug in our basis functions, which are exponentials, get a formula for the convolution of the basis functions, and that gives us essentially a formula for the convolution, which we can figure out how to implement efficiently. So this is just an example. And so having sort of an explicit basis of exponentials is nice, partially for reasons like this. Good. So there have been a variety of applications of this in the past few years. For example, streamlining certain steps in the DMFT loop using these kinds of compact grids, representing the imaginary time leg of the Keldysh contour efficiently, compressing higher order correlation functions, and others. And today I'm going to be talking about another application, which is diagrammatics. But first, let me tell you about sort of the other category of efficient representations of these functions. So the idea here is that, again, a fixed DLR basis sort of covers all imaginary time Green's functions up to a cutoff, up to like an inverse temperature cutoff at the same time. And that means that in many cases, it's going to be a suboptimal sum of exponentials representation. So for example, if our spectral function is a delta function, then G is a single exponential. And we could come up with an expansion with, okay, I've introduced this P. P is the number of exponentials, one exponential, which is now exact regardless of beta. So if only we could find this, we would have a one-term sum of exponentials expansion. So in general, finding sort of an optimal sum of exponentials approximation is a difficult nonlinear optimization problem, but there are actually kind of several very good algorithms on the market to come up with, a pretty good solution. So in our case, you can just take the sum of exponentials approximation, Fourier transform it, and we know that in Matsubara frequency, this is a sum of poles approximation. That tells us that what we're trying to solve is a rational approximation problem. And I don't want to go into the details of how this algorithm works, but there's a very nice algorithm from the applied math community, from Nick Trefethen and his group, called the AAA algorithm, which essentially aims to do exactly this. And this is a very nice algorithm. The interesting thing is it's not actually an optimization algorithm. It's not operating by kind of wiggling pole locations around and trying to lower some cost function. It's a greedy algorithm that uses a formula called the barycentric interpolation formula to sort of generate a good guess of what this should be. So I can go into that more if there are questions. We actually follow this work, which uses AAA to generate pole guesses, and then uses a little bit of optimization on top of that to wiggle around the pole locations and get an even more optimal expansion. So that's what we use in the end. So just to show you that this works, here are, okay, I've switched to delta now. But here are sort of three different, let's say, hybridization functions in imaginary time you could cook up with three different spectral functions. One is a sum of three discrete deltas, then we have a semicircular distribution, and then another continuous spectrum, which is just three Gaussian blobs. Here are the hybridizations you get at different inverse temperatures. And basically here I'm plotting running this algorithm, the error as a function of the number of poles you use. And very nicely, sort of regardless of the temperature, you see that for the discrete spectrum, this algorithm immediately finds the poles and gives you perfect accuracy for three poles. And for the continuous spectra, you get sort of nice exponential convergence. How does this compare to just using the DLR? Well, it's better. Unsurprisingly, because these are sort of fixed functions. So basically what we find is that, so we have a few different examples here. This random pole model is sort of our attempt at, like a worst case, a hardest possible case. We have a large number of random poles in our spectral function. And always you can beat the DLR by, let's say, like a factor of 2 or more. That may not sound like much, but in the next part of the talk, you're going to see that that factor of 2 goes into an exponential scaling. So we really like factors of 2 or 4. And I just wanted to mention that there are alternative methods to do this kind of thing, like Prony's method, ESPRIT. And there are a bunch of references. I'm sure I haven't gotten them all. Notice these are all sort of 2024 and 2025. Where people have used this sort of technology also in real-time calculations to do diagrammatics, analytic continuation, Bath discretization for impurity solvers of a variety of different flavors, and more. And there was actually a new method introduced, I think, a few days ago in this paper out of Emmanuel Cole's group. The take-home message here would be that if you have an application where you need a basis or a discretization of the tau domain, or the Matsubara frequency domain. The DLR is a good option in addition to the IR. But if what you really need is sort of an optimized sum of exponentials expansion for a given function, these other options are probably better for you. So how am I going to use all of this? Well, this application is sort of nice because I'm actually going to use both of these technologies in two different parts of the algorithm. So you'll sort of actually see examples of when to use one and when to use the other. So I'm going to be evaluating some Feynman diagrams, and I don't want to go into too much detail on sort of exactly where these diagrams come from. This 2010 paper describes the diagrammatic expansion we're using. This is a bold hybridization expansion of an impurity model. And I'm just going to sort of tell you the work we have to do, and hopefully this will look somewhat familiar for some people. So basically in this framework, we have, this is sort of called a pseudo-particle formalism. And the work we have these objects called the pseudo-particle Green's function and the pseudo-particle self-energy. These are sort of Green's function and self-energy in the many-body space in the impurity. So if we have n single particle states in our impurity, little n, then we call capital N the number of many-body states in the impurity, which is just 2 to the little n. And these objects, calligraphic G and sigma, are capital N by capital N matrices. There is a so-called pseudo-particle Dyson equation, which relates them. This little g is the non-interacting Green's function in the many-body space purity. And there is a self-consistency, which, that you have to solve this Dyson equation self-consistently to obtain these. Sigma can be represented in terms of delta and g via a diagrammatic expansion. And then in the end, what we want is the single particle Green's function. And there's also a diagrammatic expansion to get out the single particle Green's function from this pseudo-particle Green's function, okay? Then if you're doing DMFT, you could use the single particle Green's function to update your hybridization, send it back in here. And in this framework, we basically get sort of a simultaneous self-consistency between the pseudo-particle Green's function and self-energy in the many-body impurity space and the G and delta, the DMFT self-consistency. Okay, so that's sort of the work we have to do. Let's look at the diagrams. So this is the self-energy diagram, hybridization expansion. Maybe I should have said this at the beginning, that the sort of first order truncation of this expansion is the non-crossing approximation, or NCA, if you've heard of that. The second order truncation is the one crossing approximation, OCA. We're talking about sort of the generalization of that framework. And so now let's look at what these diagrams look like. So, okay, so here's this OCA diagram represented as an integral expression. We have our hybridization lines here. We have to basically sum over all of these impurity states appearing in the hybridization functions. Remember, this is a hybridization expansion. These Fs are basically the matrices of our creation and annihilation operators in the capital N by capital N many-body space in the impurity. And basically, we see that this diagram is telling us, at time 0, we delete a particle from the impurity, it goes into a bath, then we propagate forward in the impurity, another particle goes from the impurity to the bath, we propagate forward, then a particle comes back into the impurity, and so on, okay? And yes, so we have to sum over all of these impurity states that come in via the hybridizations and integrate over all the times of these events. So now let's talk computational complexity. Suppose we wanted to evaluate this diagram directly. Little m is the number of impurity states. At mth order, where m is the number of hybridization lines appearing in these diagrams, we get an n to the 2m scaling from this sum. Basically, we have 2m impurity state indices that we have to sum over. Then we have 2m minus 2 integrals over basically possible times that these hybridization lines can attach. So 2m minus 2 imaginary time integrals and an external imaginary time variable. So if we were to discretize this by discretize this integral by n tau points per dimension, that would be an n tau to the 2m minus 1 scaling. Then we have basically O of m matrix-matrix products between capital N by capital N matrices, which gives us n cubed. Okay, so this is the sort of direct diagram evaluation cost per diagram. And by the way, n tau, if we discretize on an equispaced grid, like by the trapezoid rule, n tau scales as O of beta, as I told you before. So we get a very nasty scaling. This is why people don't really do this beyond first and second order, except in a few rare cases. Okay, so this is what we would like to beat, and hopefully beat by a lot. How are we going to do that? We go back to our sum of exponentials. So here's our diagram. And the point that we're going to kind of observe is that these diagrams look almost, but not quite, like nested sequences of convolutions. So what do I mean by that? If this hybridization, delta of tau minus tau 1, wasn't here, then we could take this tau 1 integral and move it inside, okay? And really, this wouldn't be a double integral. It would be a sequence of two convolutions, okay? And we can do convolutions efficiently using the DLR. And for higher order diagrams, basically, if you get rid of the hybridizations, except the one connecting to 0 is okay, because it only depends on one time variable, then your mth order diagram completely decomposes into a sequence of convolutions again. So of course we have this annoying hybridization here. This is really a double integral, not two convolutions. But what can we do about it? Well, we plug in our sum of exponentials expansion. So we have this. And if we plug in tau minus tau 1, all I need to do is now use basically e to the a plus b equals e to the a times e to the b. So I can use sort of the exponential separation of variables property. This sort of looks a little complicated because there's this denominator here. So I'm multiplying and dividing by something, but really all I'm doing is using e to the a plus b equals e to the a times e to the b to separate the tau and tau 1 variables. Okay, so I get this formula in the end, and I plug that back in here. I get this, sorry, kind of complicated looking thing. Some of the orbital indices I'm able to move inside. That helps too, but since it's kind of too much to stare at once, I want you to focus on one thing, which is that I can now do what I said I wanted to do, which is move this tau 1 integral inside and get a sequence of two convolutions and a bunch of imaginary time products, okay? The price to pay, of course, is this sum over my exponentials, which is why I wanted the most compact possible sum of exponentials expansion. So I get basically p terms, but each of those is a sequence of convolutions. So I've reduced my double integral to a sum over p compositions of products and convolutions, which themselves can be computed efficiently using the DLR. So now we see the two different uses for the technologies. I wanted the most compact possible sum of exponentials expansion of my delta, and I'm willing to do some work to get it, so I use AAA. But then when I have these imaginary time operations, which I want to do, I can do those with the DLR, because I can sort of, this gives me basically a discretization of the tau space and a discretization of all my operations. It would not be fun to, do this operation, refit using AAA, do another operation, refit using AAA. It's good to have a basis in this case. Okay. So it may not actually look like I accomplished much because of this sum out front. So every time I decompose an integral, I get a sum. Okay. But in fact, this is a win in a couple of different ways. So this is just the same formula as before. Let's look at computational complexity. This was the complexity of direct diagram evaluation. Again, by moving some of these orbital sums inside, we get a reduction in this n to the 2m, but let's focus on this term, n tau to the 2m minus 1. So what do we have? Basically, at mth order, it turns out we have to separate variables in m-1 hybridization lines. Again, the one that connects to 0 is special because it only has one tau variable, so we don't mind. So we separate variables in m-1 hybridization functions. Each of those gives us a sum over p terms. So we have p to the m-1 terms in total coming out. Okay, but then each of those is now easy. It's completely decomposed. It's just a sequence of convolutions. And the cost of doing those convolutions using the DLR and some tricks, it turns out, is r squared, where r is the number of DLR basis functions, times our capital N cubed for the matrix-matrix multiplications. Okay, so there's a little more detail. We get another term, but don't worry about it. We get this complexity in the end. The other nice thing that's happened is this n tau is gone. Okay, n tau, which scaled linearly with beta, has been replaced with p's and r's, which both scale logarithmically with beta. R, I told you about, the number of DLR basis functions scales logarithmically with beta, and p, the number of exponentials in our sum of exponentials expansion of delta, is always less than r. So it also scales logarithmically with beta. So no more n tau. So kind of two things have happened. One is we've used our sum of exponentials expansion and separation of variables to reduce this rate of exponential scaling from 2m-1 to m-1, which, if you don't go to super high order, makes a big difference. And two, we've kind of gotten rid of our equispace discretizations of tau. We're using sort of compact bases to discretize the tau space. And that replaces these n taus with p's and r's, which are much smaller. Okay. And all in all, that gives you a big, big improvement over this kind of naive scheme. So, okay, so wrapping up soon, I want to show you two examples. The first one is this, well, really three examples. So the first example is this two-band model. We're solving an Anderson impurity model. This is the local Hamiltonian with a Kanamori interaction. And we basically want to take examples with off-diagonal hybridizations that algorithms like CT-Hyb might struggle with. So for the hybridization, this just says, so this is the spectral function for the hybridization. This just says there's a diagonal part and an off-diagonal part. And we can sort of adjust the strength of the off-diagonal part. And then there's a frequency dependence. And in the first case, I'm going to take the frequency dependence just to be a sum of two delta functions. Okay. This case is sort of easy for us for two reasons. One, we have a gap, so that actually makes the hybridization expansion converge more quickly. So the expansion itself is converging more quickly. And number two, this hybridization function has two poles. AAA easily finds them. So in our algorithm before, p equals 2. Okay, so we can go to sort of relatively high expansion order, bold expansion order. And basically here, so we go up to order 5. Here I'm basically showing a diagonal and off-diagonal component of the imaginary time Green's function that we get after converging this pseudo-particle self-consistency. We see sort of nice order-by-order convergence, even at relatively low temperature. And here are the associated errors where you see kind of convergence with respect to the diagram order. So at a fixed diagram order, we can do these calculations to, very high order accuracy. We could do machine precision accuracy if we wanted. It's not really necessary. We usually do like 6-digit accuracy or something. So this is the error with respect to the, of the truncation of the diagrammatic expansion. Okay, so now we do the same example, but a harder case. So we take this semicircular density, and again, this is harder for 2 reasons. One, it's a metallic system, so the hybridization expansion itself converges more slowly. And 2, this is a continuous spectrum, so we have to really test, how our AAA fitting works. So it works pretty well at this relatively high temperature and 6-digit accuracy. We only need 5 poles, 5 exponentials in our expansion. And here, basically, we see that as we increase from diagram order 1 to 5, we get convergence. I'm showing a CT-Hyde calculation, which was run for quite a while. So basically, we have a sign problem and lots of stochastic noise in this calculation. I'm also comparing to an inchworm calculation from this 2020 paper. And yes, so, we're quite close at a 5th order expansion, I would say, to the inchworm result, but with no stochastic noise. And from the timing that they reported in the paper, I would say, so this calculation at 5th order for us took 754 hours, which is quite manageable. And the timing they report is, I would say, sort of in a similar ballpark to that. So it's interesting that we can get pretty close to that result with a deterministic method with a fairly similar cost. Good. So now a more fun example. So we set up this sort of very toy model of this compound and wanted to do full self-consistent DMFT calculations. I've showed you the Hamiltonian here. I'm not going to talk too much about the physics because it's not my forte. Just sort of some key points. So this is a 3-band model with spin-orbit coupling. We're taking a very simple expression for the hybridization for the DMFT self-consistency. This is just sort of the beta lattice self-consistency. We could do something, more realistic. Basically, this model has 3 orbitals. One of them is at lower energy than the other. And we wanted to study magnetism. We wanted to study this an anti-ferromagnetic transition with temperature. So basically what was set up is we divide the lattice into A sites and B sites and have impurities associated with each of these sites, which are coupled to the bath and coupled to each other via this hybridization. Why do we do this? So then we can basically measure the magnetization on the A sites and the B sites. And here in this phase diagram, each of these dots is a full self-consistent DMFT calculation. And what we basically do is vary the temperature. At high temperature, there's no sort of magnetic ordering when we measure the magnetization. As you lower the temperature at some critical temperature, the A sites magnetize in one direction and the B sites in the other direction. So we get this anti-ferromagnetic transition. This is magnetization in the X direction. And basically here you see sort of convergence of this diagram with the expansion order. Yes, so essentially each of these DMFT calculations, because we're using this solver, was quite inexpensive. Here, this is a timing for quite high temperature. It gets more expensive for lower temperature, but at pretty high temperature, the 3rd order calculation takes 40 core hours, which is very, very manageable. So we can map out this full diagram. And just for fun, I like to show sort of how much work was done. So at 3rd order, basically what you get is to evaluate all of the self-energy diagrams once. Basically, you have 1.5 million integrals. The integrals are 4-dimensional with an external time variable, so sort of 5-dimensional. Each integrand evaluation involves 11 64 by 64 matrix-matrix products. So this would be very hard to do with direct integration, but not so bad with this algorithm. Okay, so just to wrap up, in addition to discussing this technology for compact sum of exponentials expansions, I've presented this deterministic bold hybridization expansion-based impurity solver. I think now that we have this, we can kind of explore the question of, how many applications are there for which just sort of taking this truncated bold expansion at some manageable order is sufficient, and we don't need to go to Monte Carlo. It's obviously going to be problem dependent. I've shown a couple examples here. Beyond this bold hybridization expansion, the kind of sum of exponentials plus separation of variables strategy that I've talked about, I think is applicable to, it's a general idea. I think it's applicable to other perturbative approaches. In our first paper, we described how to do this for weak coupling diagrams. We're working on generalizing this to real time. Actually, Martin Eckstein and his student sort of did this for sort of a simple model using ideas related to this algorithm. And Zhen, the student we've been working with, has written a very nice code, which we hope to kind of make open source soon as a tricks-compatible impurity solver. And lastly, let me just throw up these code advertisements. So the DLR has been implemented in many different languages, C++, Python, Julia, also Fortran, and implemented in Tricks if you want to use it. And also something which might be useful is this new package which we put out, written by Zhen Huang, called add-a-pol, which is a Python package that implements this AAA-based hybridization fitting algorithm, which I described. So that's up on GitHub if you want to check it out. So I think that's it. Thanks very much.
Thank you very much, Jason. Questions?
Hi, Jason. This is Miles. I had a quick question. This is nice work, and I wondered if maybe you covered this already in your next to last slide, but had you looked at some cases where you just stop at earlier orders, and then instead of looking at the quality of G, you just look at like a downstream property that you're interested in, like an order parameter, and maybe it already converges at lower orders?
So sorry, I pressed too many buttons and I think I've gotten rid of the talk, but sorry. But to answer your question, I mean, the last example, that's sort of what we were getting at. So if I understand your question correctly.
Mhm.
Okay, hopefully you can see this. So yeah, here we're looking at this magnetization. So and this is convergence with respect to the order. So you actually see that by second order, this has converged pretty well. It's still nice and important to have third order because third order tells us that we're converged. But yeah, I mean, here we're looking at an observable and doing what you said. Does that answer the question?
Perfect. I see. Yeah, this slide already answered it. Thank you.
Okay, good.
One quick question, perhaps, Jason. Can you give us, you mostly talked here about imaginary time, although you did mention real time. So can you give us an idea of the relative difficulty of going to real time and what can one realistically do in terms of, beyond NCA in real time?
Sure. So let me tell you about kind of the additional challenges and what's different. So In imaginary time, we basically, first of all, in imaginary time, we basically have this upper bound on the number of poles given by the DLR, okay? So we know things aren't going to get too bad. In real time, you have to do sort of on-the-fly hybridization fitting, and I would say we know less well how well this will work, though we have some ideas of what the scaling should be, and I think it's not going to be too bad. We do expect the number of poles to scale with the number of orbitals, which is not something that happens in imaginary time, so that's going to hurt a little bit. But other than that, I think, there are sort of several groups right now working on this, and Martin Eckstein has this paper out. I mean, I think this is working, and we'll see how far we can push it. But I think we'll certainly be able to do something. And, I think it's a little bit harder than imaginary time, but most of the tools basically work, and the number of poles is not too bad. So we'll see. I'm optimistic.
Okay, great to hear. Thank you.
Wang Wu, you have a question? Yang Yu, sorry.
Yeah. Hi, Jason. Thank you for the nice talk. May I ask a quick question? So, when you discretize the pseudo-particle self-energy with DR grid, do you know how to choose the energy cutoff?
Yeah, so that's a good question. So, yeah, I would say the answer is no, we don't know how to choose this a priori. One could worry that each time you do a convolution, the energy cutoff grows by just thinking a little bit about Fourier analysis. Then again, oh, did I get that right? No, I think when you do multiplications in imaginary time, you might worry that the energy cutoff grows, but then the multiplications probably help you. The shorter answer is we don't know, but we have very rapid convergence with respect to this parameter. So in principle, the right way of doing things is to basically converge your calculation with respect to this parameter. In other words, I would basically use the cutoff that works for, let's say the hybridization or the non-interacting Green's function or whatever case you're in, make a good guess, and then I would do the calculation with an increased value and make sure you get the same thing. So in practice, we have rapid convergence with respect to this parameter. This doesn't seem to get out of control for us, but maybe we'll maybe we'll find a problem where it's trickier.
Thank you.
But that's your convergence parameter. That's your N, I would say.
Jan?
Hi, Jason. Thanks for the nice talk. I'd just like to follow up on Antoine's question regarding real frequencies. I was surprised that you said it will just be a little bit more complicated, because I thought at the very beginning you used the fact that this kernel has rapidly decaying singular values if you work with imaginary times. And so why does this not constrain you to, or constrain the method to be efficient only for imaginary frequencies?
Okay, so 2 points. One is there's another thing I sort of mentioned, which is, of course, the DLR doesn't work in real time. So we're not going to use the DLR to do convolution, but we have other fast algorithms to do convolution real time. But I think what you're really asking is sort of why would we expect at all the number of poles to be under control? Is that
exactly?
Okay. So of course you could cook up examples where the number of poles is arbitrarily large. But all I'm saying is that for realistic examples, which we and other people have looked at, where let's say you have one or a small number of localized features, let's say, those things seem to be well captured using this kind of rational approximation in frequency technology. And that's known from the applied math community. So, I could come up with a counterexample by having a function which had, 50 peaks at different locations, and then I would need 250 poles or something. But if that doesn't happen, basically we have good techniques to approximate functions that seem to come up by poles. And we can make statements about scalings that have to do with, what does the scaling look like with the narrowest feature appearing in the frequency domain? And the answer is basically logarithmic in the smallest feature. Okay. So these things end up looking like basically adaptive grids in frequency, which can be extremely efficient. That's basically the reason.
So can one say, based on the examples that you've explored so far, it's looking promising, though there's no generic reason why it should always work. Would that be a fair statement?
Yeah, I would say the theorems that one will be able to prove, I think, are going to show you that the number of poles you need to capture a hybridization in frequency is going to be basically like the number of degrees of freedom that you would need to capture that hybridization on an adaptive grid.
Okay.
Which tends to be pretty good.
Yeah.
But it's
Okay,
not
thank
good,
you.
it's not going to be 5 for a
Yeah.
right for anything but a very simple function. But it might be 20.
All right, thanks.
Actually, it might be 10. That number matters.
Yeah.